Hydrogen is the most abundant element in the known universe, far surpassing helium, which comes in second. However, despite its cosmic abundance, hydrogen is surprisingly rare on Earth. This is because hydrogen atoms are extremely small and light, allowing them to escape into outer space. Additionally, hydrogen is highly reactive, meaning it readily bonds with other elements to form compounds. Some of the most important hydrogen-based compounds on Earth include organic materials and water. In fact, the Earth's oceans serve as the largest reservoir of hydrogen, storing it in the form of water molecules. Hydrogen holds immense potential as a clean and versatile energy source. It can be produced using nuclear energy in ways that provide large quantities suitable for meeting energy demands. This production method positions hydrogen as a viable alternative to fossil fuels across many sectors. Its potential applications are vast and diverse, ranging from powering cars and generating electricity to providing energy for businesses, hospitals, and homes. Moreover, hydrogen is already in high demand for industrial uses, such as the production of chemicals and steel. In a world striving for sustainability, hydrogen offers a promising solution. By tapping into its energy potential, we can reduce reliance on fossil fuels, support cleaner industrial processes, and create a more sustainable future. Whether it's fueling vehicles, powering homes, or driving industrial growth, hydrogen has the capability to transform how we think about energy. Its versatility and abundance make it a key player in the transition to a cleaner and more efficient energy economy. Green hydrogen is shaping up to be the cornerstone of sustainable energy solutions, and this is your chance to get ahead in one of the most promising industries of our time. In our course, Green Hydrogen Fundamentals, a renewable energy course, we have designed a comprehensive learning experience tailored for students and professionals eager to understand the essential knowledge about hydrogen and its application in the energy sector. Whether you're a professional looking to pivot your career into the hydrogen industry or a student passionate about building a sustainable future, this course has something for you. You'll learn the core principles of hydrogen technology and how they are driving change in the energy industry. By taking this course, you'll gain insights that usually take years of experience in the industry to acquire. Think of it as your shortcut to understanding hydrogen technologies, knowledge that will set you apart from the competition and help you stand out in job interviews or professional discussions. If you want to work in one of the fastest growing industries on the planet, now is the time to act. Hydrogen is more than a fuel, it's a revolution. And those who understand it today will lead the energy sector tomorrow. Sign up now and get the knowledge that gives you an edge. Your career in green hydrogen starts here. The link to the course is in the video description below. Hydrogen is the simplest and lightest chemical element, with an atomic number of 1. It consists of just one electron orbiting a single nucleus. You can think of this setup like the moon orbiting the Earth. The electron is the moon, and the nucleus is the Earth. Even though the nucleus is tiny, the electron orbits far away from it, making the orbital area around 100,000 times larger than the nucleus itself. This interaction between the negatively charged electron and the positively charged nucleus is what keeps the atom stable. Hydrogen also comes in different forms called isotopes. These isotopes are versions of hydrogen atoms that have the same number of protons but different numbers of neutrons in the nucleus. There are 3 naturally occurring isotopes of hydrogen: protium, deuterium, and tritium. Protium, represented as H, is the most common type, containing only 1 proton and no neutrons. Deuterium, written as squared H or sometimes as D, has 1 proton and 1 neutron. Tritium, noted as cubed H or T, is the rarest and has 1 proton and 2 neutrons. At normal temperatures and pressures, all 3 isotopes can pair up with another hydrogen atom to form stable diatomic molecules. For example, 2 protium atoms combine to create H, while a combination of tritium and hydrogen forms HT. These molecular forms are crucial for many scientific and industrial applications, as they behave predictably under standard conditions. Hydrogen isotopes are fascinating because they highlight the flexibility of this element. Each isotope has unique properties while still maintaining the essential characteristics of hydrogen. This makes hydrogen not only fundamental to understanding chemistry but also an important player in fields like energy production and nuclear science. Protium is the most common form of hydrogen, making up an overwhelming 99.9885% of the natural hydrogen atoms on Earth. Often referred to as ordinary hydrogen, protium is the simplest version of hydrogen, consisting of just a single proton in its nucleus and no neutrons. Its atomic mass is 1.0078250032 U, and it is not radioactive, making it a stable and abundant element. Protium plays a crucial role in the natural world, forming the basis of water, HO, when combined with oxygen. It is also a key component of organic molecules like methane, carbon tetrahydride, which consists of hydrogen bonded with carbon. This course focuses on the production and applications of protium, especially in the form of ordinary hydrogen gas. Now let's talk about deuterium, a heavier and much rarer sibling of protium. When a neutron is added to the nucleus of protium, it becomes deuterium. This addition roughly doubles the atomic mass, giving deuterium unique properties. Deuterium is non-radioactive and naturally occurs in small amounts, making up only 0.0115% of hydrogen on Earth. One fascinating characteristic of deuterium is that it forms a special type of water called heavy water, DO, when bonded with oxygen. While regular water is mostly made of protium, a tiny fraction of natural water, such as that found in oceans, contains deuterium. Heavy water has some extraordinary uses, particularly in nuclear science. It acts as a neutron moderator and coolant in certain types of nuclear fission reactors, helping to control the reactions safely. Deuterium also plays an essential role in nuclear fusion research, where it serves as a partial fuel for experimental reactors designed to mimic the energy-generating processes of stars. These practical applications make deuterium a valuable isotope, despite its scarcity. By understanding the unique roles of protium and deuterium, we gain insight into the versatility of hydrogen. While protium forms the foundation of life and many everyday compounds, deuterium offers remarkable opportunities in advanced technologies, especially in the field of energy. Together, they highlight the incredible diversity within this seemingly simple element. Tritium is a unique and fascinating form of hydrogen. Unlike its lighter counterparts, protium and deuterium, tritium's nucleus contains 1 proton and 2 neutrons, making it about 3 times heavier than a protium atom. When tritium combines with oxygen, it forms a type of water called tritiated water, which can exist as TO or, more commonly, HTO. What sets tritium apart is its radioactive nature. It has a half-life of approximately 12.31 years, during which it decays into helium-3, cubed He, through a process called beta decay. This process releases a small amount of energy, 18.61 keV, in the form of electrons and an antineutrino. Tritium is naturally produced in the atmosphere due to cosmic rays interacting with atmospheric gases. Specifically, fast neutrons from cosmic radiation cause spallation reactions with nitrogen atoms. resulting in the formation of tritium. However, because of its relatively short half-life, the amount of tritium naturally present in the atmosphere at any given time is extremely small, about 4 tritium atoms per 10 to the power of 15 hydrogen atoms. The concentration of tritium in natural water is even lower, making it an exceptionally rare isotope in nature. Despite its rarity, tritium can be artificially produced. One common method is through neutron activation of lithium-6, a process used in nuclear reactors. Another method involves neutron capture by deuterium, which also takes place in certain reactor environments. These production methods make tritium an invaluable resource for nuclear fusion energy. In fact, tritium, along with deuterium, is considered a critical component of the fuel required for achieving practical nuclear fusion, which has the potential to provide nearly limitless clean energy. While tritium and deuterium are essential for advancing fusion technology, they are not required for hydrogen's more conventional uses, such as chemical fuel or as a manufacturing feedstock. For this reason, the focus here will remain on the lighter isotopes, particularly protium, which are more relevant to everyday energy and industrial applications. Tritium, though fascinating and vital for specialized applications, occupies a niche role in the broader story of hydrogen's potential. By understanding its properties and uses, we gain a deeper appreciation for the diversity and capabilities of this remarkable element. Hydrogen has some interesting properties that make it both useful and challenging to work with. For instance, it has an extremely low boiling point of -252.78 degrees Celsius, which is just slightly higher than helium's, the coldest substance known, with a boiling point of -268.92 degrees Celsius. This means that turning hydrogen into a liquid for storage requires extremely cold temperatures. Even increasing pressure doesn't do much to raise its boiling point. This characteristic makes storing hydrogen as a liquid technically possible but quite complicated. In practice, hydrogen is more commonly stored as a compressed gas in vehicles rather than as a liquid. Another method of storing hydrogen involves using hydrides. These are compounds that can chemically absorb and release hydrogen when needed. Examples include saline hydrides like sodium hydride, Na, covalent hydrides such as sodium alanate, NaAl4, and interstitial hydrides like palladium, Pd. These storage methods provide alternative solutions for managing hydrogen effectively. Hydrogen gas itself is very light, with a density of just 0.08375 kilograms per cubic meter under standard conditions, 20 degrees Celsius and atmospheric pressure. Its specific volume, which is the space 1 kilogram of hydrogen occupies, is 11.940 cubic meters. Scientists use a formula called the ideal gas law to estimate hydrogen's density and specific volume at various temperatures and pressures. This law is expressed as ρ equals PRT, where P is pressure, T is temperature, and R is a constant specific to hydrogen with a value of 4124.45 J per kilogram K. However, at higher pressures, hydrogen doesn't behave exactly like an ideal gas. It compresses less than expected, which is described by something called the compressibility factor. For instance, at a pressure of 5 megapascals (MPa), hydrogen's density is about 2.9% lower than the ideal gas law predicts, and at 10 megapascals, it's 5.7% lower. Researchers can measure this compressibility factor directly and use it to understand hydrogen's behavior under real-world conditions. When hydrogen is stored in vehicles as a fuel, it is usually kept at pressures between 35 megapascals and 70 megapascals. At 35 megapascals and 20 degrees Celsius, the density of hydrogen is 23.651 kilograms per cubic meter. With a specific volume of 0.042282 cubic meters per kilogram. At 70 megapascals, these values change to a density of 39.693 kilograms per cubic meter and a specific volume of 0.025193 cubic meters per kilogram. If hydrogen is stored as a liquid, its properties change again. At a temperature near its boiling point, -253 degrees Celsius, and standard atmospheric pressure, the density of liquid hydrogen is much higher at 71.107 kilograms per cubic meter. And its specific volume is 0.014063 cubic meters per kilogram. Hydrogen is a fascinating element with unique characteristics that make it both incredibly useful and somewhat challenging to manage. One of its most notable features is its small molecular size, which is smaller than that of any other gas. This small size allows hydrogen to pass through materials that are otherwise impermeable to other gases. However, this can pose a problem. When metals or nonmetals are exposed to hydrogen for long periods, they can become brittle. This phenomenon, known as hydrogen embrittlement, makes it essential to carefully select and design the materials used for hydrogen storage and transport. Developing reliable and durable containers for hydrogen gas remains an ongoing area of research and innovation. Another important aspect of hydrogen is its safety profile. Hydrogen gas itself is generally not toxic, but it can pose a risk of asphyxiation if inhaled in high concentrations. This is because it can displace oxygen in the air, leading to a lack of breathable air. Detecting a hydrogen leak is particularly challenging since the gas is odorless, tasteless, and invisible. Unlike some other gases that spread out evenly when they leak, hydrogen behaves differently due to its extremely light nature. Being highly buoyant, it rises quickly into the atmosphere, reducing the likelihood of it accumulating near the ground. The buoyancy of hydrogen is due to its low density. At room temperature, 20 degrees Celsius, and normal atmospheric pressure, hydrogen gas has a specific gravity of just 0.0696, meaning it is only about 7% as dense as air. This property also applies to liquid hydrogen. At its boiling point of -252.78 degrees Celsius, liquid hydrogen has a specific gravity of 0.0708, making it roughly 7% as dense as water. Because of its light weight, even when liquid hydrogen leaks, it quickly evaporates and rises into the air. Despite being 59 times heavier than air in its liquid form, the rapid evaporation caused by its low boiling point and specific gravity ensures that it doesn't remain localized for long. These properties highlight both the advantages and the challenges of working with hydrogen. Its lightweight nature makes it an excellent candidate for clean energy applications. But it also requires careful handling and advanced materials to store and transport safely. Hydrogen is a remarkable element that plays a crucial role in both natural and industrial processes. One of its most fascinating abilities is its capacity to combine with carbon to form millions of compounds known as hydrocarbons. These hydrocarbons, also called organic components, are the building blocks of natural gas and crude petroleum. These resources are believed to have originated from biological matter that underwent transformation over millions of years. The vast variety of hydrocarbons demonstrates hydrogen's versatility in nature. Beyond its role in organic compounds, hydrogen also forms inorganic or chemical components when combined with other elements. A well-known example is water, which is a compound of hydrogen and oxygen. Like hydrogen, pure water is colorless, odorless, and tasteless. Interestingly, water is chemically neutral, meaning it is neither acidic nor basic, covering a majority of the Earth's surface. Water is not only essential for life but also holds promise as a renewable source of hydrogen fuel. When hydrogen fuel is used in a combustor or fuel cell, the only byproduct is water, an amount equal to what was initially used to create the fuel. Since this process produces no carbon dioxide or harmful pollutants, hydrogen fuel offers a pathway to a cleaner, more sustainable energy future. Hydrogen's ability to react with both organic and inorganic components has made it indispensable across a wide range of industries. One important application is hydrogenation, a process used to refine or improve organic materials in industries like petroleum refining and food production. For example, hydrogenation helps remove impurities or enhance the quality of oils and fuels. In agriculture, hydrogen reacts with nitrogen from the air to produce ammonia, a key ingredient in fertilizers that support global food production. Additionally, hydrogen is a powerful reducing agent. It can strip oxygen from metal oxides, forming water and leaving behind pure metals, a critical step in metal production. Industrial processes also use hydrogen to eliminate unwanted impurities from products, ensuring higher quality and efficiency. Hydrogen gas is highly flammable, making it an efficient but potentially hazardous fuel. Unlike many conventional fuels, hydrogen has a broader range of ignition concentrations when mixed with air. This means it can ignite under a wider variety of conditions, which is both a challenge and an advantage in its applications. When burned in air, hydrogen produces a pale blue flame. However, when burned in pure oxygen, the flame is nearly invisible to the human eye and primarily emits ultraviolet light. This is often observed in the operation of hydrogen-oxygen rocket engines, where the combustion produces incredible energy with minimal visible flame. The chemical reaction behind hydrogen combustion is highly exothermic, meaning it releases a significant amount of energy. When hydrogen reacts with oxygen, water is produced as the byproduct. The energy released during this process, known as the enthalpy of combustion, depends on whether the water remains as steam or is condensed into liquid. At standard conditions of 25 degrees Celsius and atmospheric pressure, the higher heating value, HHV, of hydrogen combustion is 285.83 kJ per mole, while the lower heating value, LHV, is slightly less at 241.82 kJ per mole. The HHV represents the total energy released, including the heat used to convert water vapor into liquid. In contrast, the LHV focuses only on the usable energy available for work, discounting the energy tied up in water vapor. One of hydrogen's standout qualities as a fuel is its extremely high energy content per unit of mass. This means that, pound for pound, hydrogen contains more potential energy than any other common fuel. However, hydrogen's low density presents a significant drawback. While it stores a lot of energy per kilogram, it occupies much more space than other fuels. For instance, when energy content is calculated based on volume, hydrogen has the lowest energy density of all combustion fuels. Its volumetric energy density is just 10.074 megajoules per cubic meter, LHV, and 11.915 megajoule per cubic meter, HHV. This is in stark contrast to fuels like methane gas, which has more than 3 times the volumetric energy content, or gasoline, which boasts nearly 3,000 times the energy density of gaseous hydrogen. Despite these challenges, hydrogen remains an attractive fuel due to its clean-burning nature and potential for sustainable production. Its ability to generate high energy while producing only water as a byproduct makes it a promising candidate for various applications. From rocket propulsion to powering vehicles and providing electricity, researchers and engineers are actively exploring ways to overcome hydrogen's storage and transportation limitations, aiming to harness its immense potential as a clean energy source for the future. Hydrogen isn't just a fuel, it's a way to store and transport energy produced by different primary sources like solar, wind, nuclear power, biomass, and even fossil fuels. Essentially, hydrogen acts as a bridge between energy generation and its use. Today, fossil resources like natural gas, oil, and coal are the most common sources used to produce hydrogen. However, hydrogen can also be created using electricity, another form of energy carrier. This process is done in a device called an electrolyzer. Similarly, hydrogen can generate electricity in a device called a fuel cell, making it a versatile option for energy applications. A fuel cell is a fascinating piece of technology. It consists of three main parts: the anode, the cathode, and an electrolyte sandwiched between them. The electrolyte is crucial because it allows only certain particles, ions, to pass through while blocking others, such as electrons. This selective transfer of ions is what enables a fuel cell to generate electricity. Here's how it works. Hydrogen gas enters the anode side of the fuel cell, where a catalyst, usually made of platinum, splits the hydrogen molecules into positively charged ions, protons, and negatively charged electrons. The electrolyte allows the protons to pass through to the cathode but blocks the electrons. Since the electrons can't pass through the electrolyte, they are forced to travel through an external circuit, creating an electric current. This current can then be used to power devices or even an entire electric grid. On the cathode side, the protons that traveled through the electrolyte meet up with the electrons from the external circuit. Here, in the presence of another catalyst, such as nickel, the protons and electrons combine with oxygen from the air. This reaction produces water, either in the form of hot vapor or liquid, as the byproduct. This entire process efficiently converts the chemical energy stored in hydrogen into usable electrical energy, with water as the only emission. The chemical reactions that occur in a fuel cell are straightforward but powerful. At the anode, hydrogen splits into protons and electrons. At the cathode, these protons and electrons recombine with oxygen to form water. When you look at the process as a whole, the hydrogen and oxygen react to form water, releasing energy in the form of electricity and heat. This simple yet powerful process is what makes hydrogen fuel cells so promising for the future. They provide clean energy with no harmful emissions, offering an environmentally friendly alternative to fossil fuels. Hydrogen fuel cells are an impressive technology capable of converting the chemical energy stored in hydrogen directly into electricity. The theoretical maximum efficiency of this process is about 83%, based on the ratio of Gibbs free energy to the enthalpy change, delta H, under standard conditions of 25 degrees Celsius and 101.325 kilopascals. In simpler terms, this means that 83% of the energy in hydrogen can be turned into electricity, while the remaining 17% naturally becomes heat. This high efficiency is one of the reasons why hydrogen fuel cells are gaining attention for clean energy solutions. The operation of a fuel cell depends on the type of electrolyte it uses. For example, in certain fuel cells with electrolytes like phosphoric acid or polymer membranes, hydrogen ions, protons, move through the electrolyte, as previously explained. However, other types of fuel cells, such as those using molten carbonate or solid ceramic oxide electrolytes, allow oxygen to pick up electrons and travel through the electrolyte. When the oxygen reaches the anode, it reacts with hydrogen ions to form water. The continuous input of hydrogen and oxygen into the fuel cell ensures a steady supply of direct electrical current. However, a single fuel cell can only generate a small amount of electricity due to its size. To meet practical energy needs, multiple fuel cells are combined into what's called a stack. These stacks are configured in parallel or series, depending on the desired electrical output. The total current is determined by the combined surface area of the cells in a parallel arrangement, while the total voltage depends on the number of cells stacked in series. By multiplying the voltage by the current, you can calculate the total electrical power produced by the fuel cell stack. Fuel cell technology holds immense potential for real-world applications, especially in transportation and power generation. Hydrogen fuel cell vehicles, FCVs, are a standout example. These vehicles are roughly twice as efficient as the most advanced gasoline cars, including hybrids. This higher efficiency comes from the fact that fuel cells produce less waste heat during operation. Moreover, FCVs do not emit carbon dioxide or other harmful pollutants from their tailpipes. For hydrogen combustion engines, nitrogen oxides, NO, are the only significant pollutants that need to be controlled. However, when hydrogen is used in a fuel cell, these emissions are entirely avoided. This makes hydrogen fuel cells a promising option for reducing greenhouse gas emissions and addressing environmental concerns. Hydrogen has remarkable potential as a clean fuel, but one of its main challenges lies in its storage, particularly for transportation. Compared to gasoline, hydrogen has a much lower energy density by volume. For example, a gas tank carrying 7 kilograms of compressed hydrogen at 35 megapascals can allow a vehicle to travel about 700 kilometers. However, this requires a tank with a volume of approximately 300 liters. In contrast, a conventional gasoline-powered car would only need a 70-liter tank to cover the same distance. While storing hydrogen as a liquid can significantly reduce the required tank volume to about 1/3 of a gas tank, this method has its own set of challenges. Liquefying hydrogen consumes a substantial amount of energy, and maintaining the necessary cryogenic conditions, below -253 degrees Celsius, requires highly efficient insulation to prevent hydrogen from boiling off. Finding effective ways to store hydrogen onboard vehicles is a critical focus of research and development. Currently, 3 main storage methods are being explored: compressed gas, cryogenic liquid, and hydrides. The most widely used method today is storing hydrogen as a compressed gas at pressures of 35 to 70 megapascals, which provides a storage density of about 25 grams per liter. However, researchers are increasingly interested in hydrides, such as lithium hydride, and aluminum hydride, which offer greater promise for compact and efficient storage. One innovative approach combines the benefits of compressed gas and hydride storage in a hybrid tank design. This type of system could significantly increase the amount of hydrogen that can be stored in a given volume. For example, a hybrid tank might store up to 5 kilograms of hydrogen in a 100-liter tank, effectively doubling the storage density compared to traditional methods. These advanced hybrid designs often incorporate materials and specifications tailored for high performance and safety. A typical hybrid tank might feature an aluminum and carbon fiber reinforced plastic composite shell to handle pressure loading. Inside the tank, a metal hydride core would absorb hydrogen for storage and release it when heated. Such designs aim to achieve a storage density of over 50 grams per liter while maintaining a manageable weight. A fully equipped tank might weigh around 40 kilograms and operate at a fill pressure of 70 megapascals, with a burst pressure exceeding 200 megapascals for safety. Furthermore, these tanks are being engineered to endure over 13,000 pressure cycles during their lifetime. While these advancements are promising, they highlight the complexity of hydrogen storage. Effective storage solutions must balance efficiency, safety, and practicality to make hydrogen a viable alternative to traditional fuels.